So you've got calculus and linear algebra under your belt. That's awesome, because you are way more prepared for quantum mechanics than you might think. But then you hear words like Hilbert Space and Hamiltonian, and things can get a little fuzzy. Well, that's what we're going to clear up today, right? You've wrestled with vectors, you've mastered matrices, you know your way around an integral. So what on earth is this thing called a Hilbert space? Why does it keep popping up? And what does it have to do with the quantum world? Let's break it down.
And here's the best part. The math you already know? That's the key. Seriously, we're not throwing it all out and starting over. We're just going to take those tools you've worked so hard to learn and apply them to this, well, pretty bizarre new world.
And hey, don't just take my word for it. The physicist David Tung puts it perfectly. He says that when you strip everything else away, quantum mechanics is, at its heart, really a theory of linear algebra. All that weirdness is built on a foundation you're already standing on.
Okay, so let's jump into the first big foundational idea. It's one of the core postulates of quantum mechanics, and it's this. The complete state of a system, everything you can possibly know about it, is represented by a vector. Simple as that.
Now, hold on. When I say vector, you're probably picturing a little arrow pointing somewhere in 3D space, right? But a quantum state vector is, well, it's a bit more abstract than that. It doesn't point to a location in your room. Instead, it's a mathematical object that holds all the information about a particle's state. Its position, its momentum, its spin, everything, all wrapped up into one thing.
To make sure nobody confused these newfangled quantum vectors with regular old arrows, the legendary physicist Paul Dirac came up with a special notation. He called these state vectors kets, and he wrote them like this, with this angle bracket and a vertical line, and usually the Greek letter psi inside. It's just a label, a way to say, hey, this is one of those abstract quantum state vectors.
Okay, so this brings us right back to our main question. If every possible state of a particle is a vector, then the collection of all those possible vectors has to form some kind of vector space, right? They all have to live somewhere. But what kind of space is it? And this beautifully supple phrase from a famous textbook just says it all. Hilbert space is the arena. It's the stage where all of quantum mechanics plays out. It's the mathematical world where all of our state vectors, all our kets, exist. So what's the special sauce that makes this a Hilbert space? Well, it's a very specific kind of vector space. But for our purposes, the most important rule, the entry fee, if you will, is that all the functions that live there must be what we call square integrable.
And what in the world does square integrable mean? It's all captured in this one equation. It's called the normalization condition, and it's actually really common sense. It just says that if you take the probability of finding the particle at any given point and you add up all those probabilities over the entire universe, the total has to be 1, or, 100%. The particle has to be somewhere. Makes sense, right?
Okay, so we've got our quantum states living happily in Hilbert space, but how do we get any useful information out of them? How do we actually represent the act of measuring something, like a particle's position or its energy?
And that brings us to postulate 2. It's another super important idea. Every single property you can measure, physicists call these observables, corresponds to a mathematical operator. And an operator is just a thing that acts on or does something to our Kate factor. And boom, we are right back in linear algebra territory. Remember how you can take a matrix and multiply it by a vector to get a new vector? Well, it's the exact same idea here. A quantum operator, which we write with a little hat on top, acts on a state vector, a ket. Same math, just a whole new physical meaning. Now, here is the absolute crucial connection. When an operator acts on certain special kets, which we call eigenvectors, something amazing happens. The operator doesn't really change the state, it just spits the exact same state back out, multiplied by a plain old number. That number, A, is called the eigenvalue. And here's the magic. That number is the only possible value you can get if you actually perform that measurement in a lab. Which finally brings us to the second big word you came here to understand. Because of all the different operators we could possibly talk about, position, momentum, spin, there is one that is by far the most important. The king of all operators, the Hamiltonian. And who better to cut through the fancy jargon than Richard Feynman? He once said, in his typical straightforward way, that we should really just call it the energy matrix. And that's exactly what it is. The Hamiltonian operator is all about the total energy of the system.
So the Hamiltonian, written as H hat, is the operator that corresponds to the total energy of a system. You know, the kinetic energy plus the potential energy. And if we follow our rule from before, what do its eigenvalues represent? You got it. They represent the possible allowed energy levels that the system is allowed to have. This equation right here, this is the energy eigenvalue equation. You might also know it as the time-independent Schrodinger equation. This is one of the most powerful equations in all of physics. When we build the right Hamiltonian for a system, say a hydrogen atom, and we solve this equation, the solutions we get for E are the exact quantized energy levels of that atom. This is how we can predict things like the color of light from stars with just mind-blowing accuracy.
So the Hamiltonian basically has two colossal jobs. Number one, its eigenvalues tell you the allowed energies a system can have. And number two, it's the engine that drives the whole system forward in time, using the full Schrodinger equation. It is, without a doubt, the master operator of the quantum world. You know, when you step back and look at what we've just covered, it's like we've learned the basic grammar of an entirely new language. And it's the language that physicists use to describe reality at its most fundamental level. So let's make a quick translation key to lock all this in. What we used to think of as the state of a system is now a ket vector. The arena where things happen isn't just 3D space, it's Hilbert space. The active measurement is now an operator, and the total energy of a system is captured by the Hamiltonian. See? It's a whole new vocabulary.
And I love this quote from Jean-Louis Basedevant. He reminds us that mathematics isn't just some abstract set of rules that was handed down from on high. It's a tool. A phenomenal tool that we humans have been building and refining for centuries, all in an effort to understand the world around us. I mean, just look at this. This is a 3,000-year-old Egyptian papyrus. It's basically a map of the cosmos, a guide filled with symbols that was supposed to help the pharaoh navigate the afterlife. It's a profoundly human attempt to describe and map out the rules of reality. From ancient funeral scrolls to the elegant mathematics of Hilbert space, we've always been trying to map our universe. This language of vectors, operators, and Hamiltonians is our modern-day papyrus. It's our best attempt to chart the fundamental nature of reality. And it leaves you with a pretty big question, doesn't it? Is this strange, powerful, and beautiful mathematical language our most accurate map yet?